Okay, so previously we have already derived the formulas needed for the value of Mn. So as a recap, Mn, or the nominal strength, can be solved using 0.85 F prime C, A times B sub W times the lever arm of D minus A over 2, or Mn can also be solved using As, Fs times D minus A over 2. Okay, so for the value of Fs, in some cases, so Fs is equal to Fy if steel yields, but if Fs is less than Fy, so meaning that steel did not yield. Okay, so our the next thing that we should solve for here is the value of P. Okay, so once again, for the value of Mn, we can solve for it using these equations. For the value of Mu, so you can solve for the value of Mu by using any structural theories such as three moment diagram, moment distribution methods, loop deflection method. So it would be up to you. So once again, this can be solved using mechanics of deformable bodies or theory of structures. And as for phi, guys, so the value of phi, or the reduction factor phi, is given by this equation according to NSCP 2015. So we have three categories. So we have compression controlled, transition controlled, and then tension controlled. So for the meantime, we would be focusing here on the right. So let us not look at this right now. So we will be looking at those provisions when we go to columns. But right now, we would now be discussing about phi in these formulas. But truth be told, do I know these formulas? To be honest with you, I'm not really fond of memorizing things. And from that, guys, I do not even memorize this formula here. I would rather look at the graph where these formulas were derived from. So once again, this is one graph. So from this graph, this is the graph of phi to the value of the strain of the tension bars. So in this region here, we have three categories or three zones. We have the compression controlled zone. We also have the transition zone and the tension controlled zone. When we say tension controlled, it means that tension still yields, okay? And when we say compression controlled, it means that tension still did not yield. Okay, so as you can see here, that if our section is tension controlled, meaning that the value of phi is actually 0.9. And if, let's say, our reinforced concrete section is compression controlled, meaning that the value of phi is 0.65. So what does it indicate? Okay, so for tension controlled or tension failure, so this is otherwise known as tension failure, in tension controlled or tension failure sections, the failure here is ductile. So meaning by ductile, guys, if we would be having, let's say, a ductile failure, upon failure of a concrete beam, of course, it would be bending in, let's say, this manner. You would see that the tension side would crack. So the tension side cracks, but it would be ductile in a way that it would slowly fail. It is not actually abrupt. So once again, this is ductile. So it is slower in nature, in failing. But for compression controlled, guys, tension will not yield. So meaning that if you have a certain beam here, so for example, that you have a particular beam here, the side that will fail is the compression part. So meaning in here, guys, this part here would now be failing and not the steel. And since, as you know, that concrete is not really a ductile material, it is actually brittle. And from that, guys, this would now experience brittle failure. So comparing the two, between compression controlled and tension controlled, compression controlled is very dangerous as compared with tension controlled, because if the failure is ductile, it means that upon failure, you can still go out of your homes. And well, you can still pray and whatnot. Anyway, but if let's say that your building, or let's say your beams, is compression controlled, without any warning, the beams would just fall. So that is for brittle failure. So from that, since tension controlled is more advisable manner of failure as compared with compression controlled, it means that the value of phi is equal to 0.9, meaning that for the value of 0.9 times mn, we can actually maximize the strength of the concrete. So for compression controlled, as you can see here, if the value of phi is 0.65, so phi is equal to phi mn is equal to 0.65 times mn. Since the failure here is not really advisable, so as you can see, it has a brittle failure. So we cannot really maximize its strength, and with that, guys, our factor of safety would be a lot bigger, and thus our reduction factor would be smaller for our factor of safety to become bigger. Okay, so as you can see here, that our graph is now dependent upon the strain. So for strain y, so if you can remember, strain is equal to stress divided by modulus of elasticity. So when we say strain y, this is equal to Fy over E. So meaning, guys, if we would now be multiplying the values here at the bottom by 200,000, we can also make use of this graph. So instead of you solving for the strain of y and 0.005 as the strain, you can also make use of Fy as your basis. So if you can remember that for Fs, that is now equal to 600 times D minus C over C. So, for example, that you have solved for an Fs equal to, let's say, 1,500 megapascal. So, meaning that in this case, your Fs or your Fs region is located here. So, it is, of course, greater than 1,000 megapascal. And if you would be projecting it vertically upwards, meaning that your phi is 0.9. Okay? So aside from that, guys, suppose that in your steel, the yield stress of your steel or the steel that you are using is, let's say, 420 megapascal. And when you were using this equation here, you have solved for Fs is equal to, let's say, 300. Okay? So since 300 megapascal is less than Fy, so I have indicated that my Fy in this case is, for example, 420. It means that 300 is located here, meaning that the value of phi is 0.65, meaning that it is compression controlled. So what is tension controlled? So if the value of your Fs is, of course, greater than Fy, but it is less than 1,000, meaning that it is under transition controlled. So here, so transition controlled. And if it is under transition controlled, if you would be memorizing a formula, it would now be this formula here. Or, so you can make use of this formula here in terms of strain. But the thing is, I would rather, once again, look at this graph and make use of interpolation or ratio and proportion, or better yet, I would be making use of stat mode in my calculator. So mode 3, 2. I would rather make use of this interface by my calculator. Okay, so it would be up to you if you would be making use of the strain diagram or the stress diagram, but by experience, when I was still taking my board examinations, I find this more beneficial because I can imagine it better if I would be making use of strain Fs, or sorry, stress versus phi graph. Okay, so in the next video, we will now be having a sample problem.